by Thijs Roumen on mobile fabrication. And Thijs is currently in the 4th cycle of his chemotherapy, so we're going to watch a recording of his talk, and then he's going to be online via Skype for the Q&A.
Good morning. My name is Thijs Roumen, and I want to talk with you about mobile fabrication. The key question we try to ask ourselves is, what if we had 3D printers with us anytime, anywhere? So here I am. I have a broken bike lamp, it's sagging down. And in order to fix that, I will need to have some kind of hex key to solve this problem. And I'm going to show you throughout this presentation how this can be solved using mobile fabrication. But before I go there, I would like to zoom out a little bit. If you look at the last couple of years, we saw like an exponential increase of the amount of 3D printers that have been sold. And we kind of ask ourselves the question, where is that going to lead? So this is actually the lab agenda of us at HPI, Hasso Plattner Institute. And what we do is we look at fabrication, at the history of fabrication, and try to predict what the next step is going to be. So 50 years ago, in fabrication took off in industry with laser cutters, and 30 years ago we saw the rise of 3D printers. And about 7 years ago, we made the transition, the patents of the 3D printing expired, and we made the transition towards kind of companies like MakerBot and RepRap started to kind of produce accessible 3D printers, which were adopted by a large amount of people. And an interesting question to ask yourself is like, what's going to happen next? And we cannot really predict what's going to happen there. But what we can do is we can look at a history that we are familiar with and kind of compare how that happened back then. So if we look at personal computing, and that's a timeline you might be more familiar with, we saw like in the 40s the introduction of digital computers, and then in the 60s the integrated circuits, which led to the development of personal computing, if you will. So it was adapted by consumers, and currently billions of devices are in use. Now, some interesting things that happened in that process where at some point we started to go towards mobile technology. So we saw the Park Tab and the Apple Newton, the Palm Pilot. And actually, if you look at those billions of devices, a very large amount of those are actually mobile devices. And we started to ask ourselves the question of, well, could something similar happen in fabrication? And what would that mean? Would that be mobile fabrication? And what is that going to look like? So that's the question we're trying to answer throughout this presentation. So mobile computing, let's remind ourselves shortly, allows users to access data on the go. Why did mobile computing become so successful? Why didn't we just fabricate things at home or in the lab? Well, it allowed us to respond to the situation and environment in which the user actually is. So you can imagine, or you probably did this morning when you went to go to the conference center, you looked up a map of Tokyo and figured out how to use public transport. Mobile fabrication could have something similar. So in mobile fabrication, you allow people to access physical objects on the go instead of the digital data. So we ask ourselves the same question. Why don't we just do that at home or in the lab? Well, we think that mobility allows us to respond to the situation and environment which the user might encounter, in which mobile fabrication provides a solution to their problems. So one thing that is important is that it requires the device size to get significantly smaller. But this is something that has been happening also in the past. If you look at 3D printers, they went from closet-sized devices to desktop-sized devices, and currently are actually already going beyond that. And also, it requires a vast increase of speed, which is also happening as we speak. Like the Carbon 3D is a good example of a huge speed up of fabrication. So in this paper, we partially pose a thought experiment and partially deliver a proof of concept for mobile fabrication. So we took 2 surveys in which we asked 40 people to come up with 75 tasks that require mobile fabrication. And we developed the first prototype, which is based on a small FDM 3D printer, which you can carry with you. And then developed later on a second prototype, which is based on an extruder pen. And in conclusion, we tried to ask ourselves the question, what the future mobile fabrication device might look like. So in survey 1, we asked 40 volunteers to come up with scenarios for mobile fabrication. And they came up with 75 different scenarios. And I'll talk you through 2 examples of this. So You could, if you arrive at your Airbnb, and maybe this actually happened to you in the last couple of days, the host could send you a key on your mobile phone application. You would receive that key, fabricate the key, and then actually unlock the door to the apartment. So you don't need to meet the host in person in order to get the key. Another example scenario could be that you are carrying a messenger bag, strap breaks, and you need to come up with a solution. So you engineer a solution here, in this case a carabiner, you fabricate it to replace that back strap connected to the bag, and you have a fixed solution again. So what we see in both of these scenarios, and actually in all of the scenarios that are important for mobile fabrication, we see that their scenarios are unexpected, otherwise we would have solved it before. They are urgent, otherwise you would have solved it later when you get home. And they are important, otherwise you would simply deal with the situation and not solve the problem at all. So one other interesting thing is that one of the participants mentioned that the 3D printer also needs to be carried. And on a hike you usually try to minimize weight. However, the ability to make things as needed may reduce what I need to carry in terms of emergency backup equipment. So he became very aware of the value that mobile fabrication can offer. It's a bit comparable to why NASA sends fabrication devices into space right now. So there are 75 scenarios now. Which ones are we going to focus on? We did the second survey in order to decide on that. So we had 39 participants to rate the 75 scenarios from not important to must-have scenarios. And the three most prevalent scenarios that came out of this were the Allen wrench, which I will show you in more detail in this paper, the shoelaces, replacing shoelaces, and making a carabiner to fix a shoulder strap. So now we know what we want to make. Let's see how we can make these things on the go. In order to do that, we developed the first prototype. So this is a prototype. This is a modified 3D printer. Started off as being actually a kind of smallish 3D printer of 7.5 inches cubed. But we removed 4 inches at the middle of that. So ending up with this device, which is substantially smaller. And we have the extruder head now sticking out of the device. And we added a UDO mini PC and a battery pack in order to communicate with the mobile device, with the phone. And we added the back strap so you could easily carry it as a messenger bag. On top of that, we created a solution database and wrote an app for that. Let's see how that works in reality. So here's the bike lamp scenario that we saw before. And our user is going to open his application. There we go. Opening the pervasive fabrication app. And find a couple of different solutions here. We know what he's looking for. So he's going to type here SIGCHI to find a solution that actually matches his problem. You see again, like there's different ways of solving it. We'll pick the first one. And then simply send it to the printer. There we go. So it takes 25 minutes to fabricate on this very device, and this is not a particularly fast device. So with current technology, we can already fabricate this in about a minute time. Now, solve the problem, and the user happily drives away, makes it home safely. So here is the design. So the Allen wrench that you saw there is not the most typical kind of Allen wrench that you know of. And what we did is we optimized it for speed and stability. So this is what a normal Allen wrench would look like. And this is what our Allen wrench looks like. So you see what they have in common is the tip, which fits into the hex screw. But the lever has been transformed into a truss, which minimizes printing time and material use for that matter. At the same time, if you look at the cross-section of the Allen wrench, you see that it has this L-shaped profile, which reduces the amount of material to be used and actually achieves maximum stiffness with this small amount of material used. We can push this even further by exploiting materials that the user might already carry with them, like for example a coin, and then achieve an even smaller fabrication time, as you can see here. Now, with this technology, we have one key challenge, and that's that the hex key needs to fit exactly to the nut. And with hex keys, you can kind of get around it. Like you can guess roughly what the size of a hex nut is, and if you can do that, then we made it even easier by having two tips on the Allen wrench, so you can increase the chance of guessing it right. But getting it completely right is still not non-trivial. Now, that's already true for a hex nut, but there is a finite amount of solutions. But think about other matches to the environment, like, for example, something that needs to fit into your ear. That's like impossible to guess the dimensions completely correct. So this would require high resolution 3D scanning in order to get it right. And well, we think that it's not quite ready for mobile use at this point. So we decided to take a slightly different route here. We developed a new prototype, the second prototype, which is we refer to as a human-assisted prototype, and it's based on a 3D printing pen, in this case a 3-doodler. So here's the 3-doodler with the modified battery on top of it, so we could use it on the go. We have the same problem again. The bike lamp doesn't work. You need to find the hex key. So we're going to look it up on our slightly different app this time. And in this application, you again see an overview of possible solutions. We search for the hex key. There we go. Different solutions again. Pick the first one. And now, this time, instead of a ready-made solution, you see that there is a series of instruction steps on how to make the hex key as a user. Now, the main difference between what we saw before is that in this case, we are injecting right into the hex screw. And the advantage of that is that it will be a perfect fit. There's no doubt about it. This is very important. And at the same time, so we make the lever, which is the same structure that we saw before. And we do that by following instructions projected on the phone, or presented on the phone. And the last step is to fuse the two parts together. So we heat them up a little bit and add some more filament to it. And in that way, they melt together. And again, we solve the problem, and then we can happily drive away. Now, if you look at the Allen wrench that we made this time, it actually looks very comparable to what we saw before, with the main exception that the tip is, in this case, an absolute fit and molded. So this is the key difference between compared to the previous technology. One other difference is, of course, that there is no second head, because we know that the first one will fit anyhow. So again, the key is here this on-object fabrication, because this assures a perfect fit without any measurement or guessing, and thus overcomes the limitations of our first prototype. When you're using human assistance, this also requires to have human understandable instructions. And especially for the more complicated shapes, the only way we could do that is by showing instructions on the phone and have the user trace those instructions, because then they cannot really make mistakes at all. So this is the key to get around that. Now, there are still other limitations in terms of precision and speed, but we adapted the appropriate fabrication techniques to get around these, and I will show them in more detail. So think of this scenario. Like here, we want to create a button that fits in the shirt. And the way to do that is that we made a needle and a thread out of the same piece of material. So the trick here was to extrude in mid-air and then put it away, the same way you would do that with 3D printed hair we saw last year in UIST. So you pull away, and then you have a sharp tip on top of the filament, and that tip can serve as a needle as well as the thread, which is great for this. At the same time, there's solutions where you need to have more of a strong connection, and the way we go about that is we use the raw filament. So we don't extrude this red string of material here in the shoes, but we just take the piece of filament and cut it off in the end. So we have a very strong connection in the shoe there. Another problem that you might encounter is that you want to make something that's bigger than the actual phone. Now, the way we go about that is like we trace multiple filled screens on the phone and then later on fuse them together to get, like, for example, the flip-flops that you see here in the picture. And one more thing that we did in order to use these different types of instructions is that we allowed people to create new recipes, new instruction sets. And the way they do that is they choose what type of instruction they need, and then they take pictures of the result that they achieved with it, and then our system will generate appropriate instructions that can then be used in a new recipe to, well, create a solution to a problem that you might have encountered. So we studied this to see how well people can actually use these kind of devices on the go. So we had people in the train, and we had 12 participants who each solved 2 of the 3 challenges that you see on this picture. So the 3 challenges, you saw them before actually, is to unscrew a nut, to replace a button, and to fix shoelaces. And they had to solve one of them with our solution database and one of them without our solution database, so that they find their own solution with the hardware that we provided. Now, what we found is that when people had access to a solution database, they were actually very satisfied with the solutions, and they considered the pen to be useful, and they had fun doing it. But when we took away the solution database, people were significantly less satisfied with the results, and also the usefulness of the pen was rated way lower. So we think that is because like many of the solutions were actually not as good as our solution, and that's obvious because they had to invent it on the go. Now, one funny thing is that in both cases we saw that the enjoyment has been high and equally high. So it seems that people have a good time making solutions on the go. Now, there's of course a very strong novelty effect here, so we should not put too much weight on this finding. The main finding though is that we found out that human-assisted fabrication can work if we provide users with a proper solution database. This is very important. So, in summary, we found that there is a good number of on-the-go scenarios that users actually are interested in. And we can produce many of these objects with today's technology already. Even a small FDM 3D printer can do the trick already. But the challenge is fitting to the environment. We found that human-assisted devices can close this gap and work very well in a study that we did. And on top of that, we can get an even smaller form factor and an arbitrary build volume with these devices. So what do all these conclusions mean for future hardware? We think the main objectives for future hardware for mobile fabrication are that they have to be small and mobile, they have to be fast, and they can create objects that fit with the environment in which the fabrication takes place. So the obvious thing to look at if you look at speed is the carbon 3D, which is the fastest form of fabrication or 3D printing that we currently have available. Now the problem there is that it needs to be level, so we need to find a good solution to kind of keep it stable even though you're on the go. An alternative way of approaching it would be to kind of create a small FDM robotic arm that can be mounted on the phone or could even be part of your phone. But in both of these technologies, it is super important that there is better high-resolution 3D scanning hardware that we can use on the go. And that's currently not the case yet. But aside from that, there are chances that we will have completely new technology. Because remember, we are currently with fabrication, we are in the 70s of what we saw with personal computing. So there might be a gap of like 20 years towards the actual time in which this is going to happen. And in the meantime, a lot of new kinds of technology can evolve. So on that note, I would like to conclude the presentation and give the space for questions. Thank you so much for your attention.
All right, so we have time for 1 or 2 short questions. And since this is a paper from my own lab, I cannot ask a question to my own colleague, so somebody has to go ahead.
Hi, Jun from University of Toronto. So I like the way that it can generate small objects. I guess that's also because of all the limitations you have. But I'm wondering in the future, say I have to generate a bike, mountain bike, when I'm just hiking. I don't want to hike anymore. I want to have a bike. Certainly, you can have a small, 3D printer that can print the bike, I assume. But you need the material. I'm wondering, can we in the future harvest material from the environment so that I can have a bike, make from rock and grass?
So the question was, where do you get the materials from? Can you harvest like materials from the environment?
Yeah, right. At this point, we always carry the materials with us. And I think this is also, when you're melting plastic, that is kind of necessary at this point. You could, of course, recycle models that you've already been fabricating before or models that you find around. But it needs to be of the same material at this point. Now, again, like technology is going to change, it's going to develop, so there might be more possibilities in the future. But how we did it so far has always been like carrying like little sticks of filament around with us, yeah.
Okay, one more quick question for Thijs. Anyone? Remember what Takeo said. There's one.
Hi, I'm Bruce from NYU Shanghai, and I have a question. Is that do you know there is a Kickstarter project called Olo that uses a mobile phone for 3D printing? What do you think about it?
Yeah, can you guys hear me now? Yeah, okay. So yes, we did see the Olo project, and that's a really interesting project. But what we already mentioned as one of the limitations also with Carbon 3D is that it needs to be level, and it's still reasonably slow. So yes, it's a really interesting kind of development, and we see more of these kind of mobile devices coming slowly towards the market, which is a great development, of course, also for kind of the vision that we are trying to propose. But we're not quite there yet. So it's just an interesting step forwards, yes, for sure.
All right, let's thank Thijs again for the talk.